Equilibrium. What is equilibrium? Objectives. Define equilibrium. Describe the conditions necessary for a system to establish equilibrium. Describe indicators that a system has reached equilibrium. Describe phase change and solution equilibrium. Define Le Chatelier's principle. Describe how increasing or decreasing the following factors affect chemical equilibrium. Concentration, including the common ion effect, temperature, pressure, catalyst. Reversible reactions. In earlier reactions, we considered the forward reaction in an equation and assumed all of the reactants were converted to products. For example, N2O2 gas converted into 2NO2 gas. The reaction proceeds in one direction, to the right. However, most of the time reactants are not completely converted to products because a reversible reaction takes place in which products collide to form reactants. When a chemical reaction proceeds in both the forward and reverse direction, it is said to be reversible. A double arrow is used to represent these type of equations. Rates of reaction. There are two rates of reaction in a reversible reaction: the rate of the forward reaction and the rate of the reverse reaction. When molecules begin to react, the rate of the forward reaction is much faster than the rate of the reverse reaction. As reactants are consumed and products accumulate, the rate of the forward reaction decreases and the rate of the reverse reaction increases. Here we can see, as the reaction proceeds, N2O4, the rate decreased, while NO2 rate increased. Initially, we had only N2O4, which is slowly getting converted to NO2. However, they reach a point where there is no more conversion between them in terms of no greater amount being accumulated. At this point, we say equilibrium is achieved when the rates of the forward and reverse reaction becomes equal. Concentration of reactants and products. A reaction reaches equilibrium when the concentrations of the reactants and products remain constant, even though the forward and reverse reaction continue at equal but opposite rates. Here we have N2O4 decreasing in concentration while the formation of NO2 increases. At a point where equilibrium is achieved, the concentration of N2O4 remains constant and the concentration in NO2 remains constant. At this point, equilibrium has been achieved. Equilibrium. Equilibrium refers to the state of balance between two opposing processes taking place at the same time and at equal rates. Example, the freezing of water into ice and the melting of ice back into water. Here we can see as the forward reaction proceeds, the rate decreases, and as the reverse reaction increases, it reaches a point where the rate becomes equal. So the rate is equal. Conditions necessary for a reaction to reach equilibrium. The reaction must be reversible. A reversible reaction proceeds in both the forward and reverse direction. For example, we have N2 reacting with 3H2 to produce 2NH3. Simultaneously, 2NH3 can be decomposed into N2 plus 3H2. In addition, the reaction must happen or occur in a closed system. In a closed system, nothing is allowed to enter or leave the system. In this example, we have a stopper placed above an Erlenmeyer flask. As the liquid evaporates, it reaches the point of saturation. So when one evaporates, one condenses. Indicators that a reaction has reached equilibrium. the rate of the forward reaction and the reverse reactions are equal. 2. The concentration of the reactants and products are constant. The concentration remains constant because the rate of the forward and reverse reactions are equal. There is no net change. In the first graph, as products increase, the reactants decrease. At a point where it becomes constant, we have achieved equilibrium. In the second graph, as products are made, reactants are being used up and is decreasing, and at this point, equilibrium has been achieved. To remember this, you can remember RATE and EQUAL. They're spelled using the same letter. Rate ends in E and equal begins with E. The rate is equal, while concentration is constant. This is a big misconception. Students, you need to be really careful when you discuss equilibrium, how you know when it's achieved. The rate is equal, while the concentration is constant. Physical equilibrium. Phase change. A solid liquid equilibrium at 0 degrees Celsius or 273 kelvins for water. At that temperature, water exists between a solid and a liquid. The rate of melting and freezing are equal, and the amount of ice and water remains constant. A second example is a liquid gas equilibrium for water at 100 degrees Celsius or 373 kelvins. Here, the rate of evaporation and condensation are equal, and the amounts of water and vapor remains constant. Physical equilibrium solutions. A solid liquid or a saturated solution is at equilibrium. This equilibrium exists between the dissolved and undissolved particles. It only occurs in saturated solution. In this example, we have NaCl solid being dissolved into sodium ions and chloride ions, while at the same time sodium and chloride ions are combining to form back NaCl solid. The rate of dissolving of the solid is equal to the rate of crystallization of the ions. The amount of solid and ions remains constant in the solution. For example, say a crystal of NaCl dissolves, a sodium ion and a chloride ion needs to recombine to form back or recrystallize back into the NaCl solid. Another example is gas-liquid equilibrium. This is for gaseous solutions. Here, equilibrium exists between a gas dissolved in liquid and the undissolved gas above it. For example, carbon dioxide dissolved in water. The rate of dissolving equals the rate of the gas escaping the solution. The amounts of the undissolved gas and the dissolved gas remains constant. Factors affecting equilibrium. In 1888, French chemist Le Chatelier discovered that there are ways to control equilibria to make reactions more productive. Le Chatelier principles state that if a stress is applied to a system at equilibrium, the system shifts in the direction that relieves the stress. Stresses involves increasing or decreasing concentration, temperature, pressure by changing the volume, and a catalyst. Changing the concentration. Stress. We will increase nitrogen. So the nitrogen is increased in the system. This causes the rate of the forward reaction to increase, while the rate of the reverse reaction decreases. This results in the concentration of NH3 increasing because the reaction is shifting to the right, while the concentration of H2 decreases. This reaction shifts right. A second example, we can have a decrease in stress, where we have a decrease in hydrogen. This is represented by the minus sign. The rate of the reverse reaction increases, while the rate of the forward reaction decreases. The concentration of NH3 decreases, because now we're moving to the left, while the concentration of N2 increases because we have just moved to the left and the reaction shifts left. Changing concentration by the common ion effect. Many substances dissolve or ionize in solution to produce a common ion. In an example, we have KNO3 solid, which dissolves into K plus ions and NO3 minus ions, potassium ions and nitrate ions. The stress is the addition of KCl. KCl dissolves in water to produce potassium ions and chloride ions. This increases the potassium ions in the solution, stressing the right-hand side or the product side. The rate of the reverse reaction now increases, while the rate of the forward reaction decreases. The concentration of KNO3 increases because the reaction shifts to the left, while the concentration of NO3 ions decreases because now we're moving to the left. The reaction shifts left. Change in temperature. Adding heat or increasing the temperature causes the reaction, the forward reaction, to increase because we're adding stress to the left-hand side. Now we're moving to the right-hand side. The rate of the reverse reaction decreases. The concentration of HI decreases because now we're moving to the right, while the concentration of H2 increase and I2 increase because we're moving to the right. Increasing the heat or the temperature favors endothermic reactions. Endothermic reactions, if you remember, likes heat. They take in heat from the surroundings. So increasing the heat will favor those type of reactions. Change in temperature. Removing heat or decreasing the temperature in this instance will cause the forward reaction to increase because now you have less stress on the right or the product side. The concentration of AB increases, concentration of A decreases, while the concentration of B also decreases. The reaction shifts to the right. Decreasing the temperature favors an exothermic reaction. Change in pressure by changing volume. When change in pressure is considered, the number of moles of gases only on both sides must be considered. Any solids or liquids will be ignored. Increasing the pressure favors production of substances on the side with a smaller number of moles of gas. To work an example, here we have N2 plus 3H2 to produce 2NH3. They're all gases, so we need to consider all the moles if we're going to change the pressure. The stress in this case is a decrease in volume, which causes an increase in pressure. There's 1 mole of nitrogen plus 3 moles of hydrogen, resulting in 4 moles on the reactant side. While on the product side, there are 2 moles. The rate of the forward reaction is going to increase because the system is going to shift to the side with a smaller number of moles. That is the right or the product side. The rate of the reverse reaction decreases. This results in the concentration of NH2 increasing, the concentration of N2 decreasing, the concentration of H2 decreasing. The reaction shifts right. The addition of a catalyst. A catalyst increases both the rate of the forward and reverse reaction equally. As a result, there's no net change in equilibrium concentrations. There's no shift to the product or reactant side of the reaction. Additionally, we can express equilibriums using graphs. Exploring the regions of the curve, we have between T1 and T2, the system is at equilibrium. As you can observe, the lines under the curve, it's all flat. That means it's at equilibrium. The concentration is constant. At time T2, NH3 was added to the system, as can be seen or observed with this spike in NH3. This now results in equilibrium to shift to the left because there's an increase in NH3. There's an increase on the right, so the system will shift left. Now, the concentration of H2 and N2 increases while the concentration of NH3 will decrease because it's being used up. It's being used up to make more H2 and N2. Here we can see the concentration of H2 increasing, the concentration of N2 increasing, And after the initial addition of NH3, the concentration of NH3, the amount of NH3 decreases because it's being converted over to make N2 and H2. Additionally, at T3, the system reestablishes equilibrium. The graph has become flat or constant again. The concentration have become constant. Between T3 and T4, the system is back at equilibrium.